In previous lessons, we learned about different integration techniques. In this one, we are going to talk about a kind of integral that could be used to find areas under curves. But first, let's back up a little bit and look at these differentiation notations. In differentiation, we learned that there is a notation that could be used to combine this equation and this equation into just one. And that would be the derivative with respect to x of x cubed is equal to 3x squared. Similarly, we could use a similar notation to combine this equation and this equation. And it will go this way. It's going to be d dx of x cubed at x equals 1 is equal to 3. Now, remember that if the derivative of x cubed with respect to x at x is equal to 1 equals 3, it means that the slope of the line tangent to y equals x cubed, or f of x equals x cubed, at x is equal to 1 is 3. In integration, the sort of equivalent of d dx of f of x is your integral of f of x dx. And we also have sort of an equivalent to this notation. And it looks like this. And we read it as the integral of f of x dx from a to b, or the integral of f of x with respect to x from a to b. And this is the kind of integral that could be used, as I mentioned earlier, to find areas under curves, and it is called the definite integral. And the values of a and b here are called the upper bound and the lower bound. Sorry, a is the lower bound and b is the upper bound. So instead of x, to find definite integrals, we just integrate the function using the appropriate integration technique. Then we just need to go a little bit more. We need to evaluate whatever is the resulting function when you integrate this. Just evaluate the function for x is equal to b minus the result when the function is evaluated for x is equal to a. Now let's write that down as a formula. So the first step is to integrate f of x using the appropriate technique. The result will still be a function. I'm going to call that function big F of x. The next step is to evaluate this function for x is equal to b, then x is equal to a, and then subtract the second value, resulting value from the first. So that will be evaluate f of x for x is equal to b minus evaluate the function for x is equal to a. But what does that look like really? Let's try an example. Let's say find the integral of x squared minus x dx from x equals 0 to 2. So first, we integrate as we normally would integrate a function, and in this case, the integral of x squared would just be x cubed over 3 minus the integral of x is x squared over 2. Now in the previous lesson, we're probably used to writing this as 1/3 x cubed, but actually it doesn't matter. You can keep it as x cubed over 3 or write it as 1/3 x cubed. It doesn't really matter. I would suggest though that for this one, keep it as x cubed over 3. and the other one keep it as x squared over 2. Then evaluate for x equals b, meaning, oh, it's not a to b. It is 0 to 2. So we evaluate the result for x equals cubed over 3. That becomes 2 cubed over 3 minus 2 squared over 2. This is when x is equal to 2. Now what happens when x is equal to 0? We have 0 cubed over 3 minus 0 squared over 2. And just simplify. This is 8 over 3 minus 4 over 2. And this second one here is just actually 0. So we just need to simplify this. And, okay, let's write this is 16 over 6 minus 12 over 6. And that would just be 4 over 6 or 2/3. So let's try another example. Alright, let's find the integral of the definite integral x cubed with respect to x from 0 to 2. So first, the integral of x cubed will be x to the 4th over 4. We will evaluate this for 0 to 2. So it means 2 to the 4th over 4 minus 0 to the 4th over 4, which is just 0. So really, this is just 4. And what this value actually represents, this represents the area between the x-axis and the curve y equals x cubed from x equals 0 to x equals 2. Meaning to say, let's make a quick sketch. Your y is equal to 3, y is equal to x cubed is sort of like this. Y equals x cubed. And we know that this is x is equal to 0 here. If this is where x is equal to 2, so it means that this area is 4 units squared. Let's do a simple verification. Let's find the area between the x-axis and the line y equals 3x from x equals 0 to x equals 4. Let's make a quick sketch. Okay, so let's say that's a sketch of our line y is equal to 3x. The area under the line from x equals 0 to x equals 4, let's say that x is equal to 4 is here. So what we are just looking for is the area of this right triangle, which we do not need calculus for. What we will do this in two ways. Let's use the very simple formula a is equal to 1/2 base times height. And let's check if we get the same answer using definite integral. So here, it will be 1/2. The base will just be this, and that length is 4. The height, although we are not given the height, it's actually the y coordinate of this point. The height is actually the y coordinate of this point. Although it's not given, because we know the x coordinate is 4, we just solve for y. Y is equal to 3 times 4. That is 12. So it means that it's 12 here. And that's the height. And that will be 2 times 12, so 24. 24 square units, or 24 units squared, is the area of this triangle. Now, let's use definite integral and see if we get the same answer. So really, what we are looking for here from the integral process is the integral from 0 to 4 of 3x dx. So 3x dx, I'm going to do it this way. I'm going to do it this way. I like taking out the constant, although it will still work if you just keep it as it is. So x dx. So the derivative or the integral of x to the power of 1 is just x squared over 2. And then notice that I actually forgot to point this earlier, but when we are integrating, we do not need to put the c, because when we evaluate this function, for example, when we evaluate it for the upper bound and then minus the evaluation using the lower bound, the c's will be cancelled. So that's why we don't write the c's. So it's 0, 4. And so this will be 3 times 4 squared over 2 minus 0 squared over 2, which is 3. 4 squared over 2 is just 8. And 0 squared over 2 is just 0, so it is 24. You see that we are getting the same answer. I'm going to back up a little bit on why we ignored c in the examples. Let's say we get the derivative, the integral of x cubed dx from x equals 0 to, let's say, to 2. So it will be x to the 4th over 4. Let's say that we add a c here. What happens when you evaluate it? This will be 2 to the 4th over 4 plus c minus 0 to the 4th over 4 plus c. Notice that the c's will just cancel out. So that's why during the first step, we normally just don't include c.